Everyone. Sorry, I came in a little late. I lost track of time. I looked down at the clock. I was like, uh-oh, oops. Okay. Questions? Any questions over what we did last time?
I know this is from like not the last class, but the other class. But
Okay.
does it matter like the arbitrary points? I know they're arbitrary, but does it matter like when you're trying to find a point inside the points that are plugged in, like in the line?
Yeah, so you'll have your critical numbers, right?
Yes.
And you put those on your number line, and then your test points are any numbers in between your critical numbers.
Okay.
So it doesn't matter what you pick.
All right. Okay, that's it. Thank you.
Yep. Okay, well, then today we are covering curve sketching and optimization. Next time we'll do more optimization. Exam 3 is scheduled for next Thursday. Review I will have sent out later on this week. So probably after class on Thursday, I'll send out a review, because then I'll know what to put on the review. No material from next week will be on the exam. So whatever we do next week, don't worry about that for the test. All right, let's get into this. So I told you already that when it comes to 4.4 curve sketching, that we've kind of gotten to a place in terms of technology that it's somewhat obsolete to need to go through all the steps to sketch a curve. But I did tell you I wanted to do at least one example. I might do two, where I just show you how the technique is done, where you put everything together, everything we've learned since college algebra, to be able to sketch a function. All right, so let's do an example. First of all, let me give you the steps. All right, so these are the suggested steps. These are coming directly out of our course notes. You'll be able to find this under the curve sketching section. So I just copied and pasted that. So the suggested steps for sketching a curve: first, you want to look at the function, find the domain. Then you want to find any x and y-intercepts. Okay, that's college algebra, right? Find any x-intercepts and the y-intercepts of a function. You want to check for any symmetry. So is this an even function or is it an odd function? Finding the asymptotes, if it has any. That means finding any vertical asymptotes, any horizontal asymptotes. Then you finally get to the calculus, step 5. Determine where the function is increasing and decreasing, where it might be constant. Find any local maximums and minimum values and where they occur. Then you do the second derivative. You work with the concavity, figure out if your function's concave up or down, determine any inflection points. Then you'll do this thing called make a table. I'll show you that, and then we'll sketch the curve. So these are like the general steps of how to do it. I'm going to copy this and paste it, and we're going to do this example here. I'm going to make this smaller because you will have access to these steps. So here we go. So I'd like to sketch the curve x squared over x squared minus 1. Now this would be a rational function. This is something that you would have sketched in college algebra, but how accurate you could be with it would be limited in college algebra. We can be very accurate with it here in calculus. So let's go through these steps. First thing I'm going to do is I'm going to find the domain of this function. So the domain of f, well, what I'm going to tell you what I can't have. X cannot be equal to 1, and x cannot be equal to -1. So all I'm doing is looking at that, and I'm realizing I can't have 0 in the denominator. So if I look at the denominator, the two places where it would be 0 would be 1 and -1. So I know my graph, nothing happens at 1 and -1, right? Y'all just let me know if you have a question, all right? Step 2, x-intercepts, y-intercepts. So let's find the x-intercepts first. So to find the x-intercepts of a function, what you do is you set the function equal to 0. So if I set this equal to 0, I'm setting a fraction equal to 0. And the only time a fraction can be 0 is if the top is 0. We've been through this. And then the only solution to that is 0 itself. So I have an x-intercept at 0. My graph actually touches the x-axis at 0. Now, y-intercepts, those are easier to find. To find your y-intercept, all you do is you plug 0 into the function. So if I plug 0 into the function, I get 0 squared over 0 minus 1, but that's just 0. So I have a y-intercept at 0 as well. That's basically telling me that the origin, right, the point 0, 0 is on my graph. All right, now we look to see if there's any symmetry. Now, symmetry is always a tough one. So I'm going to do it in red. Symmetry. What I would have to look for here is whether or not it's an even or an odd function. So you have to go back to college algebra and remember what it means to be an even or an odd function. So what I'm going to do is I'm going to check first to see if it's even, right? So is this an even function? Well, what that means is if I plug x in, do I get the same thing I get when I plug in negative x? Well, let's try. If we plug in x, we get x squared over x squared minus 1. The question is, does that equal what we get if we plug in negative x into the function? You tell me, is that the same thing? If we're squaring negative x, wouldn't it just become x squared, right? So these are in fact the same, right? Because this negative x squared becomes positive x squared. Sorry, I got to do something real quick. Okay, so yeah, this negative x squared right here becomes positive x squared. This negative x squared becomes positive x squared, and so they are the same. So it's an even function, which means that I have symmetry, that this should be a reflection. I should see a reflection of the graph over the y-axis. That's what even functions look like. So if you reflect them over the y-axis, they will land right on top of themselves. Cosine of x is an example of an even function, in case you've forgotten. Cosine looks like this. And so if you reflect that over the y-axis, it would land right on top of itself. So it's an even function. I'm just giving you an example of an even function. So when we graph this, we should expect to see the same thing happen. All right, asymptotes. So step 4, I want to find the asymptotes. So let's start with the vertical asymptotes. I'm going to put VA for vertical asymptotes. Is that all right if I don't write that down?
I have a question.
Yes.
For symmetry, why are we only checking for even and not odd?
Okay, because you can only be even or odd or neither. So if you're 1, then that's it, you're done. So if you're even, you're even. If it wasn't even, I would then check for odd. And
Okay.
if I was odd, then I'm odd. If I'm not odd, then I'm neither, which means you're done, which means you shouldn't expect any sort of symmetry.
And for odd, you would check for the y then.
For
Actually, what would you
odd,
check for?
For odd, here's what you would check. You would say, is f of negative x equal to negative f of x? That's what you would be checking. Is plugging in a negative into the function equal to putting a negative out in front of the function? I can give you an example of an odd function. F of x equals x cubed. That's an odd function. Why? Well, when I plug in negative x, that's negative x cubed. And when I cube a negative number, I get that thing negative, right? I don't need the parentheses anymore. But that's exactly what I would have gotten had I just put a negative in front of the original function, right? Put a negative in front of the original function, and these two are equal. And therefore, that would be odd. Does that make sense, Ash?
Yes. Yes, it does. Thank you.
Okay. And the type of reflection we would see here would be a double reflection. It would look like a reflection over x and then y. An example of that would be sine. So if you graph the sine function, there's sine. What would happen if I reflected over y? So it would look like that, right? But now reflected over x. And if you reflect that over x, you get this. But that is just the back end of the sine function. I mean, that's exactly what sine looks like. So double reflection. They call that, they actually technically call it a reflection over the origin. That's what they call it, but it's really a double reflection. It's reflection over Y and X. Good?
Yes, thank you.
Okay. All right, so vertical asymptotes. To check for vertical asymptotes, what I'm looking for, and this is some calculus thinking here. I'm looking for, is there anywhere in the original function where the numerator would be a number, fixed number, but the denominator would go to 0 or be 0? So how about at 1? Right? If I plug in 1, isn't the bottom 0 and the top is 1? So we would have fixed over 0, which would become a vertical asymptote. And then also at -1, if I try and plug -1 in, I'm going to have a problem because it'll be -1 squared over 0. So in both of those cases, I have vertical asymptotes at x equals 1 and also at -1. Why? Because we get fixed over 0 when we try and plug one of those in. What about horizontal asymptotes? Horizontal asymptotes tell you about what's happening on the edges of your function, right? The edges. So we have a way of doing that now in calculus, right? We can talk about the end behavior of a function by doing a limit. If I take the limit as x goes to infinity of this function, that should tell me what the function's doing as I go out to the right forever. So what is happening if I let x go to infinity here? I get infinity on top and bottom, don't I? So what can I use?
Hospital, whatever his name is.
L'Hopital.
The hospitals, right? So I'll do L'Hopital here. Derivative of the top is 2x. Derivative of the bottom is 2x. And 2x over 2x is 1. Which means that as the graph goes out to the right, I should asymptotically be approaching 1. Now, on the other hand, if I go out to the left, which means I go to -infinity, out the left side of the function, the exact same thing happens. I get infinity over infinity. So I apply L'Hopital's rule, and I already know what's going to happen. I'm going to get 2x over 2x again, which cancels out, and you just get a 1. So as I graph this thing out to the left and to the right, it should be headed towards a y value of 1. So my y value should be approaching 1 on both edges. It should be the same, shouldn't it? Didn't we say this was an even function? So whatever's happening on the right should happen on the left. It's a mirror image of itself over the y-axis. Questions on that? What's next? Determine where the function's increasing, decreasing, and constant. So now I'm going to take a derivative, right? I'm going to take, for step 5, I want to know where my function is going up, where the function's going down, right, etc. So I'm going to figure out what the derivative is. And the derivative of this function is going to require quotient rule, right? Take derivative. So I'm trying to find the critical numbers right now. The derivative of the top times the bottom minus derivative of the bottom. I don't know why I did 2. It should be 2x. Sorry. Derivative of the top is 2x times the bottom minus derivative of the bottom, which is also 2x, times the top, which is x squared. All of this over the bottom squared. Okay, that's my derivative. So what we're doing now is what we did last class, right? Well, actually 2 classes ago, where we're trying to find where the function goes up and down. So I need to now take the derivative, figure out where it's 0, and then I also need to figure out where the derivative doesn't exist. Those are the 2 things I'm going to look at now. Look at that derivative. Let's clean it up. I should have cleaned it up here. 2x cubed minus 2x. I know I'm moving fast, but I'm also on video, so you can always go back and watch this. Okay, so when I do the top and I distribute the 2x through there, looks like I'm getting those 2x cubes are going to cancel out. That's nice. So all I get is -2x on top and then x squared minus 1, that quantity squared. There's my nice clean derivative. I want to know where this derivative is 0, so I just set the top to 0. And I get one solution there, 0, right? And then on the other part, I need to know where it doesn't exist. And there are actually 2 places it doesn't exist, 1 and -1, right? Look at that derivative. You cannot plug 1 or -1 in here. But 1 and -1 aren't even in the domain of the function, are they? They're not in the domain of the function. So how are we going to deal with this, right? Because these are not in domain, not in domain. So technically, they are not critical numbers. So now I would go and get my number line, right? So when I do my number line, watch what I do here. The only critical number I have is 0, right? That's the only critical number I have. But something is happening at 1 and -1, because remember, those points are not in my domain. At 1, my function's not defined, and at -1, they're not defined. So what I'm going to do is I'm going to have to pick test points here, 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 and here, just to make sure that when I go from from the left of -1 to the right of -1, I need to make sure that I don't have a change in my increase and decrease on the function. So some good points here like -2, yeah, -1/2, and how about 2? And where are those numbers getting plugged into? What am I doing with those? Plugging them in where?
F. Right?
Into where?
F? Is it F or
What are we checking? We're trying to see whether or not the function goes up or down, right? And so we're always investigating the first derivative for that. So if the first derivative is positive, we're going up. If the first derivative is negative, we're going down. So we want to plug those into F prime. So I'm going to test those over here on the side. I want to do F prime of -2. I want to do F prime of -1/2, F prime of +1/2, and F prime of 2. And all I care about, right, is whether or not I get a positive or negative. That's it. That's all I care about. So I'm going to go to this version of the derivative right here in yellow. Okay, that's what I'm going to be using to test. What can y'all tell me about the denominator of this derivative, no matter what?
Cannot be 0.
It can't be 0, right? But because it's squared, won't the denominator always spit out a positive number? So all I really care about is what's happening in the numerator, right? So what happens if I take -2 and I plug it in there for x? -2 times -2, +4, right? That's positive. So I know that I get a positive here, which tells me that my original function must be increasing there. So back here in the table, I'm going to go f must be going up here. What happens at -1/2? Same thing, plug in -1/2. -2 times -1/2 is positive, right? 2 negatives multiply to be positive. So I will stay positive here on the derivative, which means my original function is still going up, increasing. And then you do the next two. And without showing you or thinking through it, I'm gonna just tell you what they are. They both turn out to be negative, which means I'm going down, and then I'm going down again. So function goes down, function goes down. Questions? We're only 20 minutes in on this problem, okay? Do we have any local maximums or local minimums? Do that over here. Do I have a local max?
yeah?
Okay, yeah, it goes up and down, right? We're going up here and then down here. And zero, it's happening at 0, and actually 0 is in the domain of the original function. So this is a local maximum. If 0 was not in the domain, be careful here. If 0 was not in the domain, this would not be a local maximum. You can only have a local maximum or minimum when you go up and down or down and up at a point that's in the domain of the function. So here 0's in there. So I know that when I plug 0 into the original function, we already checked earlier, when I plug 0 in, it spit out 0, right? So that's my local maximum. How about local minimum? Do I have a local minimum? Does it ever go down and back up? No, none. Okay. Step 5 done. I figured out where my function goes up and down. I figured out any local maxes and mins. Isn't this fun? Step 6. Find local, increasing, oh, sorry, this was step 6. I apologize. This is step 6 right here, local max and min. Step 7, determine the intervals where the function's going concave up and concave down. So now what I'm going to do, this is last class, is I'm going to basically work with the derivative. Here's the derivative right here. I'm going to take that, and I'm going to be taking the derivative of that to be looking at the second derivative. So let me now move that in here. Paste. This is step 7. I want to know where the original function's concave up. I want to know where the original function is concave down. I also want to know any inflection points, right? Okay, so this is our first derivative right here. And now what I'm going to do is I'm going to take the derivative of the derivative. Yuck. Okay, here we go. I'll do it in brown. The second derivative of this function, quotient rule, is the derivative of the top, which is -2, times the bottom, which is x squared minus 1, the entire thing squared, minus, now when I take the derivative of the bottom, it's chain rule, right? Because I have x squared minus 1 squared. So when I do that derivative, I've got to first bring the 2 down, then x squared minus 1 to the first power. I don't need the first power there, but I'm putting it. Then times the derivative of what's inside. So the derivative of x squared minus 1 is 2x. But then times -2x, because that's the first function, or the top function. And all of that divided by the bottom squared again. So x squared minus 1 squared, but then squared again. So it's going to turn into the 4th power on the bottom. How we doing? Y'all liking it? Equals. Watch me clean it up. Okay, I'm going to leave that alone right now. I'm going to put the 2, the x, the negative, the 2, all of the stuff in yellow, I'm going to put together. So that should give me a +8, right? Because 2 times 2 times 2 is 8. And then I have 2 negatives there. They're going to become positive. So 8. And then I should have x and x go together to become x squared. And then I had the x squared minus 1 next to it in parentheses. All that divided by x squared minus 1 to the 4th. Okay. That looks terrible. I see a GCF though. Do y'all see that there's an x squared minus 1 here and an x squared minus 1 there? And I can pull one of them out. So let me pull that out. Also, do you feel like pulling a number out? I could pull a 2. Do y'all want me to pull a 2 out of these? Yeah. How about a -2? You want a -2 or no? Just 2? I don't care. I see Ash saying, yeah, let's pull the -2. -2 is going to come out. I'm also pulling an x squared minus 1. Okay, what is still here? Well, I pulled the -2, right? And I pulled one of these factors of x squared minus 1. See, there was 2 of them here. So I pulled one of them, which means there's still one there. So there's still an x squared minus 1 there. I pulled the negative out of this 8, so it's going to be minus, and then the 8 becomes a 4. And I didn't pull this x squared out, right? I didn't pull any x's out. So I still have an x squared. And then I did take this x squared minus 1 and pull it out. And there's nothing left, right? So that's it. And that's all over x squared minus 1 to the 4th. Couple of things algebraically I can do now. one of these factors cancels with one of those down there, and that becomes a 3. That's like having an x over x cubed. You can cancel one of them. And then up top, I can actually put this together. I don't need the parentheses there. That's really x squared minus 1 minus 4x squared. So I get, what the hell's on top? -2 is still there. Then in that parentheses, I have a -3x squared minus 1, I believe. So I just put those two together. And then all of this over x squared minus 1 cubed. Oh my goodness. I don't like the negatives on this. Is this okay if I pull a -1 out of this? I'm just going to pull a -1 out of that. That'll change that to a positive. It'll change both of those to positives. I don't know. I just didn't like the way that looked. Okay. There's my second derivative. So now I'm going to play that same game I just played a minute ago with the first derivative. I want to know where it's 0. And I want to know where it doesn't exist. Let's do the doesn't exist first. 1 and -1 again, right? Because the denominator will be 0 at 1 and -1. And I'm going to throw those away because not in the domain, right? So those technically cannot be critical numbers. How about the derivative being 0? Set the top equal to 0. Can that ever be 0? Can that ever be 0? We can divide both sides by 2. That can't be 0, can it? Look, if I subtract 1 on both sides, I get -1. If I divide by 3, I get -1/3. And there's no number that I'm ever squaring and getting a negative number, right? Nothing. So I have no solutions here to that, right? No solution. So on my number line, I don't have any critical numbers here. I don't have any critical numbers here. But again, just like the first derivative, I do have something interesting happening at -1 and 1 because those points are not in my domain. And those are vertical asymptotes, right? We knew that from step whatever it was up there. So that will allow me to pick some test points. -2, 0, and let's go 2. And these are going to be plugged into, I'm testing those into the second derivative, because the second derivative is what tells me concavity. Where's my second derivative? Right here. I'm going to copy this, bring it down here so we can see it. So there's my second derivative. We have to test these. So let's be careful. What can you tell me about the numerator? What will the numerator always be?
Even. Or sorry, positive.
Positive, right? Because look, I'm going to square a number. It's going to be positive. Multiply by 3, still positive. Add 1, still positive. Multiply by 2, still positive. So my numerator is always positive. Always, always positive, right? So all I really care about is what's happening on the denominator. So let's plug -2 in here. What would happen if I take -2 and square it? I get 4. Take away 1, I get 3. 3 cubed is 27. That's positive. So that means that when I plug in -2, I get a positive number here, which means the original function is concave up. It's smiling, right? Positive people smile. So I'll come over here to my chart and I'll put concave up. Now, what happens if you plug in 0? Well, we know the top is positive always, right? But what happens when you plug 0 in here? 0 squared is 0. Take away 1 is -1, right? -1 cubed is negative. So this is going to be a negative number, which means my original function is concave down here, which I would put f concave down like that. And then when you plug in 2, you're going to get positive. And that means that your original function is concave up. 32 minutes in. All right. Do we have any inflection points? Careful, careful. We do go from concave up to concave down, don't we? But they're happening at -1 and 1, which are not points in the domain. The only way you can have an inflection point is if that point is in the domain. So even though it looks like I have inflection points, I do not. All right, so no inflections. No inflection points because -1 and 1 are not in DOM F. Okay. What's the next step? That was step 7. Step 8. Okay. Step 8 is what's called make a table. And I may have shared this with some of you. I don't remember if I shared this with the whole class. Did I tell you all that story about that guy that didn't like me, that came in and when I was a teaching assistant doing calculus? Did I tell you all that story? All right, I won't get into it too much. He didn't like me, and basically he thought I was getting problems wrong in class because I wasn't simplifying them all the way down to look like the back of the book. And so he came and like barged into the tutoring lab and like made a big scene and told me I needed to like apologize, and it was just a mess. I was like 22 years old, 23 years old. He was like 28 years old. I think he just didn't like me because I was younger than him, and he just didn't like it. So he was trying to tell me I was wrong. And I wound up showing him that it was just algebra that he didn't know how to do. And so he didn't like me. And this step right here, where you make a table, I don't do it the way any textbook has ever shown it to me. Like, I do it my own way that I think it makes sense to me. So when I showed my class this method, or when I showed the students this method, he didn't like it because it was my way. So he named the method. He named it, and I still use the name today. Because in the very first day I told them, you know, y'all can call me Robert, y'all can call me Rob, you can call me Mr. D Giovanni. Just don't call me Bob or Bobby, because I don't go by Bob or Bobby. Like, no one calls me Bob or Bobby. So he called this the Bobby method. Okay. So I'm sharing with you the Bobby method. If you go to a tutor or a textbook, you're not going to see this. It's not going to look like this. Okay. But I think when I show it to you, it's going to make perfect sense. Hopefully. We'll see. All right. So what we're going to do now is we are going to put all this information together to draw a picture. All right. And I'm going to use the Bobby method to do it. Ready? Here we go. I don't remember that guy's name. Wish I did, because I would actually call it his method now. Like, whatever his name was, I would call it his method. All right, so y'all ready? Here's what we're gonna do. Our graph is gonna go on this page. So I'm gonna go ahead and just act like I've got some graph paper here. All right. Now, I'm gonna start, I'm not drawing the graph yet, okay? And keep in mind, I'm gonna use this whole page, all right? So what I'm gonna do first is I'm gonna draw a number line. And then what I'm going to do is I'm going to go back to where I was figuring out where the function was going up and down. Okay, that was step 5, I believe. When I was on step 5, I did this and I made this table, right? You see this table I made, or not this chart right here? The numbers I have on this chart, not the test points, the numbers were 0 and -1 and 1, right? I had three numbers there. So I'm going to put those on mine. And I'm going to space these out a little bit. That's going to be 0. And let's say this is 1. And let's say this is -1. All right. Then I'm going to go to the other one that we did, which was the second derivative. And on that one, the only points I had here were -1 and 1, right? Those are the only ones I had. So I make sure that those are here. And they are, right? I have -1 and 1. Once I've got, so basically what I'm doing is I'm putting the critical numbers and the important numbers from both the part where I'm figuring out where the function goes up and down and the concavity. I'm putting them on a number line. Now what I do is straight up from each of those, I'm going to go up and create, I'm going to create a table from this. And the table is going to have 3 rows in it. It's going to have a bottom row, the middle row, and the top row. All right. I'll always do 3 rows, okay, for every problem I ever do. On the left side, I'm going to write over here, just kind of as a guide, I'm going to put F prime, and then above that, I'm going to put F double prime, and above that, I'm going to put F. Now, I know that seems like a weird order, but I'm going F prime, F double prime, F, okay? And now I would like for us to go back to step 5, and I would like for us to look at step 5, the up and down of the function. This came from the first derivative, right? This was the first derivative that gave us this information. We go up, up, and then at 0, we go down, then down, right? So I'm going to put that on my table. To the left, my original function goes up here, then up, and then at 0, it switches and goes down, and then the function goes down. Y'all agree? Up, up, down, down. Now, the next row, I'm going to go look at my second derivative information. My second derivative information was the concavity. And I was concave up to the left of -1, then concave down all the way from -1 to 1. Do y'all see that? All the way from -1 to 1, I'm concave down. And then I'm concave up again. So let me put that on my table. I was concave up here, right? And then at -1, it switched over. Now I'm concave down, right? And then am I concave up here or concave down right here? Still down, right? Because I don't switch until I get to 1. So we're concave down again. And then we go back to concave up. Y'all see what I'm doing here? Any questions? You sure? Now the final part. We got to figure out what F is doing, the original function. So to figure that out, what I'm going to do is I'm going to combine both of these pieces of information together to determine what's happening up here. So if I tell you that you have to be going up, but you also have to look like a smile, right? That's what concave up means. Don't draw this. If I tell you you have to be concave up, right? Smiling, but you have to be increasing. Can you be on the left side of the smile? No, you have to only be on the right side of the smile, which means that these two pieces of information together tell me that my original function here looks like this. The right side of the smile. Now, when I get to this piece, I look and I have to be going up, but concave down. So am I the left side of the frown or the right side of the frown? Left or right? If I have to go up and be frowning.
Left.
Left side. So it's got to look like this. Okay. Now I have to be going down the frown. So the only way to be going down the frown is to be going on the right side. Yes. So now I've got to look like this. And then when I get here, I have to be going down the smile, which means I have to be the left side of the smile. I can't be the right side of the smile. Okay. You got it? That's the Bobby method right there. That table right there. Most textbooks do it with what's called a sign chart, and they check like positive, negative, and if you have 2 negatives, then that means you're doing smile. It's a mess. I don't like it. All right, so now we're ready for the graph. So here comes the actual graph. I'm going to try and draw this. I'm going to zoom out just a little bit. Okay, here we go. Here's my y-axis. Here's my x-axis. Okay, let's go back to the very beginning of the problem. We have a domain problem, right? -1 and 1. We have an x-intercept of 0 and a y-intercept of 0. I'm going to go put that on my graph now. I'm going to go put that x and y-intercept on there. So I'm going to draw my graph in green. That point lives on my graph, right? That point lives on my graph. All right. The other thing I know is that I have an even function, so it should look like a reflection when I finish drawing this. I'm going to keep that as a mental note. I have two vertical asymptotes, one at 1 and one at -1. So I'm going to put those on here. Where's 1? 1's right here. Notice I lined it up with the 1 that I have up here, and my -1's over here, lined up. Oh, I didn't go the same distance. I just realized that. Oops, sorry. It's okay, we'll be fine. So what I know is that I have vertical asymptote here, so I'm going to put vertical dotted lines here, like that, right? And then what else do I know? Horizontal asymptote, right? Didn't we have a horizontal asymptote? When we go out to the right, it heads to 1, and we go out to the left, it heads to 1. How am I going to put that on my graph? Well, I'm going to go up 1. Let's just say that this is up 1, okay? And I'm going to put a dotted line out here like this, and I'm going to put a dotted line out here like this, and I'm going to remember that when I draw my graph, I have to go towards that. Okay? Do I have anything else? That's pretty much it, right? That's all I have, right? All this information, I already know about all this information. Oh, I have a local max at 0, 0, right? I do have a local max, but this should be enough for me to draw the graph, okay? This should be enough. Well, actually, I see I have a problem. I can draw this middle piece. Watch me draw the middle piece. I know that I have to be at this point in the center, right? And notice that to the left of it, I have to look like this piece right there. So that means the graph's going to have to look like this. And asymptotically go down because of the vertical asymptote. And then on the right side, it's got to look like this, which means it's got to go and do kind of like the same thing over here, like this. Now, let's go over here to the right. I know that the graph looks like this, right? It's got to look like this because of that shape, but I've got to approach that dotted line. So I know that I've got to go up on the left because I've got a vertical asymptote. And on the right, I've got to flatten out. So it's got to look like that. And then over here, it's got to look like the same thing. Flatten out and go up. So do you all see how these pieces match? All that matches up, right? Now-
How do we know that the middle is in the bottom of the line of the x-axis?
Okay, because you know that this point exists, right?
Yes.
Okay, so, but you have to draw this, right? You have to draw this shape, which means you have to come out to the right and curve down. You have to look like the left side of a frown. So there's no way that it could come up, right? It would have to go down. Same thing with this right side. It has to look like the green, so you can only go down. It can only be decreasing and frowning. That's it. We're done. 46 minutes. So this obviously, like I said, is obsolete, right? This is very obsolete. Let's see how long it takes me to do it with a computer, right? X squared divided by x squared minus 1. Done, right? But before computers, and I will admit, this is a pretty generic, pretty simple vanilla like function. It's not complicated. The derivatives were pretty clean. It's, you know, it's not that bad. But more complicated functions, we need a way of doing them, right? So what I would recommend you do, because we don't have time for me to do like 8 examples of this, right? What I would do is I would try, look at the book, look at the textbook. The textbook gives you, the textbook gives you 3 examples, 3 of them. I did the first one. The next example in the textbook is x e to the x. I suggest you just look through the textbook, read through the steps, and see if it all makes sense what they're doing. All right. And then the one after that, the third example is this one, cosine X over 2 plus sine X. This one is really complicated because they're not giving you a closed interval. So when you start setting things like set the numerator equal to 0, set the denominator equal to 0, you're trying to solve trig functions which have infinite numbers of solutions. And so what you wind up getting is some pretty crazy stuff. Let's use a calculator or a computer to graph that one. Cosine X divided by 2 plus sine X. That's the graph of this one here. So if we did this by hand using calculus, look at all the local maximums, right? Those are all local maximums. These are all local minimums. You would have an infinite number of them. You would also have like concave down turns into concave up, right? Still concave up, but then turns back into, well, where's my color? Back into concave down. So you have inflection points. Do y'all see that? Bunch of inflection points. So read through the book. What I plan, if I give you anything on this, if I were to give you anything like this on a final exam, if I did, it would be a very generic function, probably like a polynomial. In the homework assignment for this, the first like problems 1 through 6 are all polynomials. That's the most I would ever give you, because again, I think that this is sort of obsolete at this point. Okay. But at least you've seen just how much work it is. It's a lot of work to try and graph a function by hand. Ash, do you have a question?
When you say a polynomial, does this division problem count as a polynomial?
The one that we did
Mm-hmm.
would be a rational function. So no, it would not.
Thank you.
The polynomials are even easier because the
Right.
derivatives are much cleaner. There's no quotient rule. It's all just power rule. All right, that's it. I'm moving on because I don't want to do any more of that. All right. We could literally spend the next 8 weeks doing sketching functions by hand. All right, we could. And some of the problems in there at the end of, so the homework assignment for this is really, where is it? Curve sketching. I would say just ignore all these problems. Maybe just, 1 through 5. 1 through 5 odd, or just 1 through 5. I don't foresee that this would be something that would come back to haunt you. Like in Cal 2, this isn't going to come back to haunt you that you didn't do this complicated curve sketching. All right, it's not. All right, we got to move on. So we're going to move on to the next topic. Now, this topic is absolutely needed as you move on. If I could argue that this is probably one of the pinnacle topics of the class, and that's optimization. All right. It's like, why have we learned all this? What is something we can do with all this calculus, right? And optimization is probably the most important thing. Related rates, optimization, those two are pretty close to one another. But I think optimization is probably the most important. All right, so once again, we reached a point where we can apply what we've learned so far to something interesting, word problems, applications. So I do give you a basic set of steps here, all right? And I'll run through these steps with you as we do a problem. So let's not get bogged down on the steps right now, all right? I want us to start this by thinking about something, all right? So clear your minds for a moment, all right? And I'd like for you to think about this. I'm going to go build a fence, okay? In my backyard, I'm going to build a garden for my wife, all right? And what she's telling me is that, you know what? We're going to build a fence and we're going to build a rectangular garden like this, just a rectangle. And what she tells me is she wants it to be 100-foot perimeter. And the 100 feet of perimeter, the reason why she told me 100 feet is because that's how much material we're willing to buy, right? Because you got to build the fence, you got to go buy the fence material. She's like, okay, 100 feet of fence, that's wood is so expensive. That's as big as we're going. And she wants me to build this thing, right? This garden, 100 feet of fence. What I'm interested in is how should I build the fence so that the garden has the most area to it? Now, area is a different measurement than perimeter, right? Perimeter is the distance around something. Area is the distance inside of it. So my question is, how should I build this to get most area? So does it matter though? Like, does it matter? If you only have 100 feet of fence, then can I build it like any way and I'm still going to get the same area each time? Let's do a poll. Let's see if you understand the question first. I have 100 feet of fence, right? I can build it different ways, right? I can make these sides different lengths. It still has to be a rectangle. So my question is, do the dimensions of the rectangle, if I use all 100 feet of fence, do the dimensions actually impact the area, or am I going to get the same area no matter how I build it? That's the question. Am I going to get the same area no matter how I build it? Yes or no? Am I going to get the same area no matter how I build it? If I have to stick to 100 feet of fence. Jeopardy music in the background. All right, final Jeopardy. We have our results. Not from everybody, but close to everybody. Here are the results. It's about 50-50 in terms of the responses. About half of you think, you know what? It doesn't matter how we build it. All right. We're going to get the same area no matter how we build it. And then half of you say, no, it does matter. You are going to get different areas depending on how you build it. So I'm going to convince you very, very easily with a diagram. Look at this right here. Right now I've built the rectangle and I've used 100 feet of fence. So this is 10 feet by 40 feet by 10 feet by 40 feet. So do y'all agree that that adds up to be 100 feet total around? But the area, which is the calculation of how much space is in here, is determined by taking that and multiplying by that, right? So the area is 400. So that's one scenario, right? That's one scenario. Let me change it though. And let's see what happens. If I change it to there, 13 by 37. If you add these up around the outside, you'll still get 100. But now look at your area. It's gone up, hasn't it? If I go the other way, make it smaller, maybe I make it 5 by 45. So 5, 45, 5, 45, all the way around, that's 100. But look at my area now, 225. I've almost cut the area in half, haven't I? By doing it that way. So how do I build it to get the most area? Keep an eye on this number, 400. 481, 500, 600, oh, 625, and then it starts to go down. You see? It looks like the best way to build it is that right there, which is a square, right? To get the most area, it looks like I need a square. So the big takeaway from this is that when I'm constructing this, I don't just say, oh, 100 feet around, doesn't matter how I build it. We'll get the same area no matter what. I hope I've illustrated that it does matter and that there is an optimum solution, right? There is a way to optimize this to get the most area out of that 100 feet of fence. I've shown it to you visually. How do we do it with calculus? right? How do we do it with calculus? So you understand the problem? We're going to solve this with calculus. And then we're going to do a harder problem because this is like a baby problem. All right, so let me bring up the steps. So first you need to read and understand the problem, right? Read and understand what you're trying to do, right? You want to draw pictures, okay? Draw pictures. You want to introduce notation. You want to determine, and this is the thing that's real important here, you want to determine the variable to be optimized. In other words, find this thing that I'm calling the objective function. So what is the objective of this whole thing? What is trying to be optimized? Once you've done that, what you need to do is express the variable to be optimized in terms of other variables. Use the given restrictions and information to express the variable to be optimized as a single, in terms of one single variable, and then use the methods of this section to solve the problem. Now, all of that seems crazy until we do an example. All right, so let's just do this one. So does everyone understand the problem? Got 100 feet of fence. We want to get the most area. Want to get the what? Most area. Get the what? The maximum area. Maximum area, right? Maximum, maximum. Do we know how to find maximums of things? Yes. We can find maximums of functions. So we need to somehow express the area as a function of a single variable. So my objective is to find the maximum area. All right, well, let's write down what we know about areas of rectangles. The area of a rectangle is length times width. Right, we all agree with that. Length times width, that's area of rectangle. Now what I'm going to do is I'm going to start introducing notation and variables. So if I call this side X, that would be my length, and I'll call this side Y, that would be my width. Then another way I could express the area is the area is X times Y. You agree? I want to figure out how I can make that area be as big as possible, as big as I possibly can. Well, now what we have and what we have to consider is whether or not we have what's called a constraint. A constraint. Do I have a constraint? So generally speaking, this rectangle can have any width, can have any X and any Y dimension. Just if I say, hey, draw me a rectangle, you can make it be as long as you want and as wide as you want. You have no restrictions. But here we do have a restriction, don't we? We have a restriction that the perimeter has to be 100, right? So my constraint is that the perimeter of this thing must be 100, right? That is a constraint within this problem. What is the perimeter of this rectangle in terms of X and Y? So if I asked you to give me a formula for the perimeter, if you had to walk around this thing, right, start walking, you would have to walk X, then Y, then X again, then Y. So wouldn't the perimeter really be 2X plus 2Y equals 100, right? Y'all following this? So far, so good? Got to go to a new page. I want to just pause and just kind of go through everything again. We understood the problem, 100 feet of fence, got to build this thing. I want to get the most area. So we're trying to maximize the area. So my objective is maximum area. I write down a formula for area. Then I get that area formula in terms of some variables. Right now, I'm trying to find the maximum area, but do you notice that area right now, in order for me to know area, I have to know two things, X and Y. Y'all see there's two variables there? When we've been finding maximums of functions, we've always had functions of one variable, right? I mean, think about what we did last class. Everything that we did trying to find maximums of functions, right? Find the maximum of this function. There's only one variable in there, X, right? It's the only variable in there. Right now, we don't know how to find maximums of things that have two variables, only one. So we have to figure out, is there a way, can we get this? Can we get this to one variable? Can we? Well, we have a constraint over here, right? Look at this is a constraint and it has the variables X and Y in them, just like this has X and Y. So could you solve this over here for Y? If I asked you to solve this equation for Y, could you? Let's do it. Let's divide everything by 2, make our lives easy. So this becomes X plus Y is 50, right? And now let's solve for Y, so Y is 50 minus X. What I can do with that, if that's what Y has to be, I can replace that Y in the equation with 50 minus X. And now what I have is a new formula for area. It's X times 50 minus X, right? Which means that my area is 50X minus X squared. Is the area now a function of one variable only? Yes. Can we find maximums of functions of one variable? Absolutely. So I want to now stress to you that this area is a function of X. So I'm slightly changing the notation there because I want you to understand that we have kind of reached our goal here. We have figured out a formula for the area as a function of a single variable X. And now what we want to do is find the maximum of that. Questions? This is where we meet. This is where on these problems you're at not a crossroads. You're at a split now in the road. You have to make a decision of which path to go. When we were looking at maximums and minimums, we had 2 different methods. We had a method for closed intervals and we had a method for open intervals. So you have to now determine, is there a restriction on X? Because X is the variable, right? Is there a smallest value that X can be or a biggest value that X can be? So go back up and think about this. You're going to build the rectangle, right? Tell me about the smallest value X could be. What's the smallest side I can make on that rectangle? I see Ash saying 1, 2.
Point something, something, something. It's right above 0, technically.
Could it be 0?
No,
Could it be 0? Why not?
because then it would just be 0 as an area, wouldn't it?
Then you'd have a 0 area, right? And my wife would be pissed, right? But 0 is an actual, it is possible. I could, right? If I made X 0, then the Y's would have to each be 50, wouldn't they? So it's like, I'm going to lay this out. I do 50 here, and then I do 50 here. But then I have to bring those 2 together and I don't have an area, right? That would be stupid for me to do that. But it is possible for me to do that. I should get fired for it, but I could do it, 0. So that means that I could look at this between 0 and what would be the maximum I could let X be? And you have to be careful with this. What's the biggest X could be? It's not 100. It's what?
99.999 whatever.
No. X represents both sides of the pen, right? That I'm building, or the garden. So if I say that X is 100, if I said X was 100, then that would imply that I had 200 feet of fence, because I need X for both sides. So the biggest X could be here would be 50. Now, again, it would be stupid because I'd be using all the fence for the X's and I had nothing left over for Y, right? But these are like extreme cases. But what it gives me, those extreme cases give me a closed interval, don't they? Closed interval. Which means I'm going to use the closed interval method. This is where I was saying, when you're doing these problems, you get to a point where you have to choose, is this a closed interval or is it an open interval? And you have to think about the geometry of the problem and the variable in it. Any questions on that? How do we do closed interval method? Take the derivative, right? Find the critical numbers. So take the derivative of this function. Boy, that derivative is nice, isn't it? 50 minus 2x. Now we take that and we figure out where it's 0 and where it doesn't exist. So where's that derivative 0? Where does the derivative not exist? Right, well, it never not exists, right? Because the derivative is actually a line. 50 minus 2x is linear, it's polynomial. There's never any domain issues. But where is it 0? Well, take it, plug in, solve for x. So I'll move to at negative 2x to the other side. I'll divide by 2 and I get 25. Hey, spoiler, we already know the answer, don't we? Wasn't it 25? 25 by 25? That is the answer, but you have not proven that to me yet. You have not proven to me that that answer is the best. Okay, what do you have to do next? You take that number and so we're going to take this number 25 and we're going to take what other two numbers?
Extreme.
The 0 and the 50, the two endpoints, and we're going to plug those numbers into
Number line. Oh, no, the A prime, sorry.
Derivative.
derivative.
Yes.
You sure?
No,
Closed
the
interval
original
method.
function.
Original function. See, this is where things start getting weird. People, like, I mean, it's normal. This is where calculus students start forgetting what's getting plugged into what. When you're in the closed interval method, you're taking your critical numbers and your endpoints, and those are going into your original function. And the biggest number that comes out to your max, and the smallest that comes out to your min. You only go to the test points and plug into the derivatives if you are on the open interval method, which we are not here because we have a restriction on x between 0 and 50. So I'm now going to evaluate the original function at 25, the original function at 0. Sorry, not f. I should put a. The original function was a. And then the original function at 50. The original function I'm highlighting here in green, right? That's what we're going to be plugging into. Why? Closed interval. That's why we're doing it. So let's plug in 25. If we plug in 25, we get 50 times 25 minus 25 squared. And if you do that arithmetic, you get 625. And then you plug in 0, which is really nice because that's just 0. And if you plug in 50, you get 50 times 50 minus 50 squared, which again is 0. Remember, those are those two cases where my wife went out and slapped the shit out of me because I used all 50 feet on both sides and left nothing for the other sides, right? So those are the extreme cases where I get 0 area. But I can guarantee you that this one right here is the one that gives me the maximum, right? I've now shown that and we're done. So the dimensions, what are the dimensions of the pen? We know what x has to be, right? This is what x is. What is y going to be? 25 as well. How do you know that?
Because it can, like the top is 5.
That's right. You can go to this right here. Remember the constraint? If y is 50 minus x, and we just said that x had to be 25, then y would have to be 50 minus 25, which means y has to be 25 as well, which means you're building a square. You could also say this, okay? Let's say you wanted to put a table in your dining room, okay? You want to build a table in your dining room to have people sit at it. If that dining room table has to have a fixed perimeter, okay, whether it be 100 feet or 10 feet, then the best way to do it, to get the most area out of that table, is to make a square. If you make a rectangle, anything that's not a square, you're not maximizing the space, but that's if you have a fixed perimeter. Here's a question we're not gonna be able to answer yet because we still have more to do, but here's a question for you. What do you think gives you better area? Taking a circle that has a circumference of 100 or taking a square that has a perimeter of 100? Which one of those do you think gives you more area? They both have the same distance around them. What do you think's better, a circle or a square?
Square.
What's that?
I said a square.
You think it's a square? So they have the same perimeters, So if you walk around, if you start at one point, start walking around, I'm telling you that's 100 feet, 100 inches, whatever you want. And then this one, if you start walking around, it's also 100. It turns out that the circle's the better way to go. You'll get more area out of the circle. Now I have to prove that to you. I can't just do it like this, but it's just to get you thinking, like, how would you prove that? We will, if I have time, maybe next class, not today. All right, so let's just take a look back. Okay, let's relive this. My wife wanted a garden. We had 100 feet of fence to use. Build it so it has the most area. Most what? Area. Maximize what? Area. Objective, maximum area. Find a formula for area. Okay, that formula generated some variables, X and Y. I had an equation for area, but it had more than one variable in it. So I had to somehow get it to one variable so that I could do calculus. Well, I had a constraint. I knew that I had a fixed perimeter. So I solved for Y, replaced it in here. That was a nice polynomial function. I figured out it was a closed interval. And then I did my closed interval method. I evaluated at the critical numbers and the endpoints. The biggest number out was my max. Boom, I'm done. All right. We good? All right, we're going to change the problem now. After I'm on my way to the store to go pick up the lumber, my wife calls me. She says, you know what? Sorry, I misspoke, okay? Instead, what she wants me to do is she wants me to build that garden, okay? But she wants it to have an area of 100 square feet. So she's not telling me anymore how much fence I have. She's telling me that she wants the inside of this to have an area of 100 feet. Okay. Now it's up to me to go up to the hardware store and figure out how much fence to do. Does it matter how I build it? There's a lot of ways I could build it to get 100, isn't there? So I have an animation for you on this. I think I did. No, I don't. I'm so sorry. I thought I did. I'm gonna have to update that. I should. So does everyone understand the problem? She wants 100 square feet for area, and I've got to figure out how to build it. So here's one option I could do. I could do 5 by 20, right? Would that have an area of 100? Yes? Everyone agrees? Yes? Okay, so what's the perimeter of this? How much fence would I need to build this? 20, 20, 5, and 5. So what's that?
50.
50. I need 50 feet of fence to build that. That's one way I could do it, right? I could also do this. I could do what? Well, obviously I could do 10 by 10, right? Yes. I hope that's obvious. 10 by 10. That would give me 100. How much fence am I going to use here?
40.
40. All the way around, right? A square. That's better, right? That's more efficient, isn't it? To do it this way than that way. And then there's some other extremes. Like, what if I did it this way? What if I decided to do 2 and 50? I could do that, right? 2 and 50. That would give me 100 square feet. How much fence am I going to use here to go around?
104.
104. Right? Fence is expensive. I definitely don't want to go buy 104 feet of fence, right? If I could do 50, but I don't want to do 50 if I could do 40, right? What's the optimum way to do this? What is the optimum way to do this? What is the optimum way? This section is called optimization. We are trying to figure out the best way to do something, right? The best way, the cheapest way in this case. So the big question is, yes, I could just go with that right now. Okay, I could. Without any calculus, I say, hey, that looks better than everything else. But how do I guarantee myself that that's the best answer? I have to do the calculus, all right? So here, let's do it. I'm going to build my thing here. I know I want to find, what am I trying to do? I know, okay, let me write this down. I want the area of this to be 100 square feet. What's the objective here?
Find the minimum X value.
Find the minimum, not maximum, minimum what?
X value, like variable, the minimum
Okay.
size of the fence.
The minimum
Perimeter.
perimeter. We want to find the minimum perimeter. This is a different problem than the previous problem, right? In the previous problem, we had a fixed perimeter and we wanted to find the maximum area. Here, we have a fixed area and we want to find the minimum perimeter, right? Totally different problem. They look related. I mean, they are connected. They have the same geometric shape, but they're very different in terms of what's going to happen here with our function. So we want to find the minimum perimeter. So let's write down a formula for the perimeter. Well, the perimeter, I'm going to need to label some things. Let's call this X and Y. It doesn't matter where we label them. That's X and Y. Then what is the perimeter in terms of X and Y? We already talked about this, right? 2X plus 2Y. This is my objective, is to try and figure out if I can make this as small as I can. But right now, it has two variables. Little side note here, right? Two variables, not happy. I need one variable. Little side note. Calculus 3 is called multivariable calculus, or calculus of multivariables. And what that means is that in Cal 3, you actually learn how to do what we're doing right now with functions that have more than one variable, like X, Y, Z. You can have, 3 variables, 4 variables. And you can do this without having to do what we're doing in Cal 1, which is here we have to get everything to one variable. But in Cal 3, we can actually have techniques to do it where we still keep the 2 variables the way they are. Multivariable calculus. It's, down the road for some of you, maybe. We have much more powerful methods is what I'm getting at. Okay, now, how am I going to get this to one variable? What have I not considered yet?
Constraints.
The constraint. I do have a constraint. I can't build this however I want, right? I need my wife to be satisfied. So my constraint here is what? What must be what?
The area must be
Area.
100 feet squared.
Yep, the area must be 100 feet, 100 square feet, sorry. So the area of this must be 100 square feet, right? But what is the area of this in terms of what I've drawn here? Like as a formula, area would just be what?
XY.
X times Y, right? So this X times Y must be 100. Now this X times Y must be 100 allows me to go to this equation that I'm trying to optimize, find the minimum of, and replace either the Y with something that has X's in it, or I can also replace the X with something with Y's, but let's just solve for Y. So if I solve for Y over here, I have to divide both sides by X. Agreed? And now I can take that and replace that Y in there with it. So the perimeter is now 2X plus 2 times 100 over x, which means that the perimeter is now a function of just one variable. It's 2x plus 200 over x. My perimeter now only needs one variable in order for me to determine what it is. Questions? Have y'all ever heard that poem, "Two roads diverged in a yellow wood, and sorry I could not travel both, but be one traveler long I stood, looked down one as far as I could, to where it bent in the undergrowth"? Did y'all ever heard? I hated English in grade school and I had to memorize that poem, and I still have it memorized. I hated it so much. Anyways, you are standing, two roads diverged in a yellow wood. You are standing at the divergence of the two roads. You have to figure out, is this closed or open? And it's not a guess. It's, you got to think about this. Is there a smallest value x can be? You have to have an area of 100. You have to. So could x be 0?
No.
That's not possible, right? Because if x is 0, that means the y would have to be, think about this picture. If I make this x go to 0, but I have to have an area of 100, doesn't the y have to get really long? In fact, y would have to go to like infinity practically. Look at this right here. Look at your objective. I'm sorry, the constraint. You see the constraint there? It kind of tips you off right here. X can't be 0. If x is 0, you have division by 0, right? You have division by 0. So you can't let x be 0, right? So I'm not going to be on a closed interval. Is there a biggest value x can be?
$100.
If x is 100, I could go bigger. Let me just challenge that. I mean, you're thinking right. Okay, I can do it this way, 100, right? And that would have to be 1. Now I've got it. I've got the 100 square feet, but could I make it 200? That would have to be a half then. And now they multiply to be 100. I could even go 400, right? And now I've got 1/4. And that's when my wife is slapping the shit out of me, right? She never slaps me. It just sounds fun to say it. Okay. She kicks me, punches me. No, I'm kidding. I could go as big as I want, right? Because I could make the other side get really, really small. Now, would I ever build it that way? Absolutely not. But I have to take into consideration that I can make x theoretically go as big as I ever want. And the y just keeps shrinking. So mathematically, we go to infinity here. The big thing is that this is open, okay? It's an open interval, which means we can't use the closed interval method, which means we have to do what we've been doing like the last 2 days. We've got to figure out, does this perimeter function ever go down then back up, right? Does this perimeter function go, does this perimeter ever go down and then follow it by an up? Because if it goes down and back up, then I will have found a minimum, right? So that's what we have to do now. This is fun. All right, so here we go, open interval method. The setup is pretty much the same. I have to take derivative, right? My derivative is 2, nice, minus 200 over x squared. Okay, how did I get that derivative? Well, derivative of 2x is 2, that's fine. I thought about this 200 over x, and I really wrote it as 200 x to the negative 1. I brought the x up, and then I took the derivative. So when I take the derivative, the negative 1 comes out, makes it negative 200. Then I subtract 1 from the power, it becomes x to the negative 2, and then I dropped it back down. Is that okay? That's my derivative. I need to figure out where that derivative is 0. I need to figure out where that derivative doesn't exist. All right, where's the derivative 0? Well, Oh, crap. I gotta do algebra then. Right, I've got to figure out when that's 0. I'm gonna get a common denominator. So all I did there was just multiply the top and bottom of 2 by x squared. And that way I could push them together, right? That's what I did, x squared here, x squared here. And now I just have to set the top to 0. And then solve for x. Move the 200 over, divide by 2, and take the square root. I'm throwing one of these answers away. Which one?
Negative.
Negative, right? X can't be negative. X is the length of one of the sides of the garden, right? So I'm not going to have a negative. So x equals 10. That's a critical number. Now, what about the derivative over here? Is it ever not defined? 0, right? X is 0. However, that's not in our domain, right? You're not allowed to plug in 0. We already said that up here. Now what? Now what?
Plug it into the derivative,
Plug what into the derivative?
the critical number.
Careful.
No, sorry.
We're plugging something into the derivative, but not the critical numbers.
Is the
Doing
number
the number line.
Yeah, we need the number line and then test points, and then the test points go into the derivative, right? Yeah, see, it's a lot to keep track of, all right? So I'm going to draw a number line. My critical numbers are 10 and 0, right? Now, I'm putting 0 here because I want to remind you that to the left of 0, nothing makes sense, right? Because x has to be bigger than 0. We don't want to go to the left of 0, or else, again, I'm not going to call my wife and say, hey, I'm going to make it negative 10 feet, but you're right. I mean, it doesn't make sense. So I only have really 2 test points I need. Something here, how about 5? Something here, how about 20? And those are going to get plugged into the derivative, right? The derivative, because this is where we're trying to see where it goes up and down and up. So I'm testing. I'm going to do f prime of 5, and I'm going to do f, not f, damn it, I did it, sorry. It's, what's our function called? P prime of 5 and P prime of 20. Here's your derivative highlighted in blue. There it is. And I want to test that there. Shall we plug in 5? Sure. 5, let's see. 5 squared is 25. 200 divided by 25 is 8. 2 minus 8 is a negative number, right? So that means that I get a negative here. What does that tell me about the P function to the left of 10? The P function is
Decreasing.
decreasing. P is going down here. Ooh, that's very good to see. If it goes up on the other side, we got a minimum. In fact, we've got the only minimum because there's no other regions for us to look at. This is the only place where we have a minimum, where we would have a minimum. Let's plug in 20. 20 squared is what? 4,000? 20 over 4,000. Yeah, take 2 minus that. That's gonna be a positive number. Do the arithmetic yourself. It's positive here, which means that the perimeter function goes up here. And that tells me that at 10, we have a local minimum. But again, because the graph has to go down and up, and it never comes back down and up again, that's the only minimum I have. So that is the minimum value of the function. So x equals 10 is where we'll get a minimum. Then what is y? How are you going to tell me what y is?
Plug it into whatever.
right there,
The other
into the
thing.
constraint, right? That's how you can get y. And y here would be 10 as well, because you plug 10 in and you get 100 over 10 is 10. So my wife calls me up. I want a garden. Okay. I want it to be 100 square feet. I'm going to go build her a square, 10 by 10. Now, look, I realize you're sitting there going, duh, like I would have done that too. I didn't need to spend 20 minutes doing a calculus problem to do that. Okay. I get that. So why don't I give you a problem to think about? I'm not going to assign any homework from this section yet. All right. Oh, I want you to work on those graphing problems, those curve sketching, the few that I gave you to look at. I want you to work on those. But I also want you to work on this problem, right? This one problem. I want you to think about it by the time we come back to class next time. All right. So I'm going to keep it very similar to what we just did. Let's say that I don't, but let's say that this is a river. Okay, this is a river. Okay. And my wife and I have some property off this river. We don't, but let's just act like we do. All right. And she's like, you know what? We're going to get some chickens and we're going to build some pens for these chickens. And the chickens, we're going to put them next to the water so they can drink, and then we'll feed them and everything else, whatever. So what she would like for me to do is build a pen that comes off the river like this. And she wants to keep some of these chickens separated. So what we're going to have is I drew that a little bit too big. We wish to build 4 identical pens, right? Each with an area of, how much room should we give these chickens? How about 12 square feet? All right. So each pen has to be 12 square foot, each one of them. And they're identical. So whatever this first pen looks like, they all look like. All right. Find the dimensions which uses the least amount of material. How much material would you need? These are 2 different questions. The first one is just, hey, what are the dimensions of the pen going to be in order to use the least amount of material? And then I want to know how much material you would have had to have used. Right, that should be a question, huh? So a couple of things I need to point out to you. On these pens, everything in brown has to be built, okay, as part of the fence. But these pens up against the river, we're not going to build a wall. We're just going to let the chickens, they're real scared of water. So they're just going to like drink and they won't go anywhere. So you don't have to build a wall. There's no construction that's needed along this side. Okay, you can, if you want, don't do a river, do like a cliff. Okay, so they're not going to go over the edge. So you only need pins, you only need structure here. Understand? See if you can figure out how to build this so that each pin has 12 square feet, but you use the least amount of material possible. And then tell me how much material that is. Do you understand the question? It's the exact same question as the one we just did, the one right before this, but your formulas are different. See how it goes, all right? See how it goes. I do have an issue. I may have an issue with my office hours today. I apologize ahead of time, but I will be available today later on. So let's see, at 4 o'clock, if I'm going to have an issue of conflict, I will open the session up, but I'll put a note there when I'll be able to be there. So I apologize ahead of time. I just found out about this right now. So any questions? You know what your homework is? Okay, good luck. Have a good day.
Thank you.
Have a good day.
Bye.
Thank you.